here. Oops. Okay, as you can see here on the left, basically that's what the computer sees, right? It sees a matrix with numbers, and then the computer has to determine what's in the image. And so basically, if you look at the pictures, for us it's very easy to see that there are cars and cows, but if you look at what the computer sees, it's actually far from trivial, because it has to figure out where in this set of numbers the car is, right? So if I give you this image, you have no idea what's going on there. And then even more difficult is if you have video, so then you have a stream of these images, and you have to determine, for example, where in the image an action occurs. Okay, and so today there are quite a lot of applications. We're actually lucky there are a lot of applications around which do start to work really well. So we're probably all aware that in most of your cameras there's a face detector. It works reasonably well, not always, but in most cases it helps you to set the autofocus. It's also the first step for face recognition. So if you pass the border control, there's a face detector and recognition algorithm which recognizes the face and sees if it's you. Another application is search for places in particular objects. So you can go around with your smartphone, take a picture, for example, of the Golden Gate Bridge, of any art picture, whatever, and you can then get a description out what's actually in the picture. And then another application, which is currently very, very in vogue, is basically car safety and autonomous driving. So there again, visual perception is one of the keys. You have to detect the pedestrians and the objects which can be obstacles on the road. And in addition to that, you want to see what the pedestrian is actually doing. So that there comes in action recognition, right? You want to say is a pedestrian walking towards the road? Is a pedestrian standing, running? Is a child? Or whatever. So that gives you an idea if the car should stop, slow down, or do something else, okay? Another application which is very popular is video surveillance. So basically what you want to do here is you want to see what the people are doing and detect some kind of abnormality. So if somebody puts, for example, down a bomb, you want to detect that automatically. Okay, and so coming back to why is this difficult? So why is this difficult? If you just had one template, it would be fairly easy to detect this template in a set of numbers. But what you have, if you have an object, you can see the object under for different camera positions, emulations, and viewpoint changes. And so here, concretely, what does it say? Basically, here you can see the same bridge taken with a change of the focal length of the camera. And then if you look at these two images, they're significantly different, so you cannot just match them or overlay them or compare the pixel one by one, right? And this gets even more severe in the case of viewpoint changes. So here you can see that the church is seen from the front, from the side view, and it gets even more difficult if, for example, you see the church from behind, then matching these two objects is really difficult. And then another problem are lighting changes and occlusion. So here you can see that basically you have this grid overlaid over the church, and so it's far from trivial to say that these are the same buildings. So this is the first set of problems. And then this was to detect one specific object. And then if you want to go even further, what you want to do in visual recognition is to determine a class or a category. So for example, to say, this is a car, this is a face, this is a chair, right? And so in this case, the set of variabilities increases even further. To all the viewpoint changes and so forth come the different appearance configurations, right? So if you look at here, if you see that these are all different chairs, they have almost no similarity, so it's really hard actually to learn or construct a model for the class chair. You'll see in a moment how actually we do this. And then if you go to video, another example, this gets even more difficult. So here, for example, you can have a viewpoint change. The person is standing, eating an apple while standing, and then here somebody is feeding a person. In both cases, the people are eating, right? So you can see basically visually, if you just look at the low-level visual information, there's basically nothing in common. And then here another example for eating. So here you have a monkey eating, actually, and then here this would be a classical dining table sequence where people are eating. And again, you can see that basically these are completely two different types of eating instances. And in the end, you would want to assign the same label to these two videos. Okay, and so just like to step back, what was actually the evolution of visual perception? So basically, it has evolved a lot over the past 30 years. So basically, in the early 80s to the early 90s, what people used to do, they had simple features, handcrafted models, and the approaches would work for a few images and simple tasks, right? So what they did, they extracted a set of edges and key points, and then did some 3D matching or 2D matching of the models to the images. And you can see that basically this is not very discriminate, it's not very robust, it's not robust to failures of the extraction. And then another similar approach, which was very popular, was based on projective invariance. So the idea here was, again, to extract conics and lines and rectangles from the image, and then based on these geometric entities to construct invariants which were invariant to 2D projective transformations, right? And so again, this was not very discriminative and highly not robust to noise. And maybe the lesson which was learned from this time was actually that invariants are a powerful mechanism for describing information in images and videos. And so basically, the idea here is that you have the same value under geometric transformation, geometric and photometric transformation, which are geometric transformations. The simplest one is translation, just the plain translation of the image, rotation of the image, and then more significantly, a scale change. And just to give a simple example, so if you have a similarity transformation which transforms this configuration with rotation, scale, and translation, what's a simple geometric invariant would be the angle and the length ratio, right? So basically, under this transformation, the angle and the length ratio stay the same. Another example would be if you want to be invariant to scale changes. So here, you have to just normalize the region in some way by estimating some invariant scale properties, and then you can describe this normalized region by normalized descriptor. Okay, and then basically people from the early 90s to 2000, they moved away from these very simple edges and lines. Also, computers got a bit more powerful, and models were now based on global appearance descriptors, right? So for example, one work for face recognition by Turco and Pentland was based on the mean and the eigenvectors. And so here the idea is each face was expressed by the mean over the collection of faces and the coefficients for the different eigenvectors, right? And so this allowed to compress the representation and then find the closest face in the subspace of faces. And so why was this working potentially better? Because here you had this discriminated information which was based on the appearance. And another work which then moved one step further was to not have these global appearance descriptors, but to move to local appearance descriptors, make them invariant, and this allowed for the first time to recognize in a small collection of images, so here 1,000 images and objects transformed on the scale and rotation and in the presence of occlusion. This was then later extended to scale invariance and gave rise to the popular SIF descriptor, which is robust to different types of rotation scale changes. And again, it allowed to recognize for the first time objects in cluttered scenes, okay? So that was in the early 2000s. And so basically here, what you have a matching approach, which matches, you construct descriptors which are invariant to different transformations, and you match these descriptors robustly to the images. So there is no learning. And so basically the next step was actually to add machine learning to these low-level descriptors. And one of the first works by Viola Jones, they took Haar wavelets, so the image was described by Haar wavelets, which could be computed very fast by integral images. And then on top of that was a machine learning approach based on boosting for feature selection, okay? And this was one of the first approaches for face detection. So here they trained a profile and a frontal face detector to be invariant to these viewpoint changes. And here, if you look at the features which were selected for the profile detector, you can see that these are kind of characteristic regions on these profile images which allow to detect or to say if this patch contains a face or not, right? So what they could do then is to detect in almost real time faces in an image, okay? So this was one of the first approaches which used machine learning in combination with features. And so basically, starting in the early 2000s, there was a whole line of work which evolved and combined basically image features with different machine learning techniques, okay? And so the idea here is very simple. We have a set of negative and positive images, and what we want We want to describe them in some way or the other. So this is the feature, that would be the image feature. And then we want to learn a decision boundary which separates the positive from the negative images, okay? And what's important here was how do we construct the appropriate features? So what the research questions was, how do we construct the appropriate features? What are the best machine learning techniques? And then something which became more and more important over time, what are actually good examples to capture the variability of the visual world? And then just what do you do once you have learned this classifier? Then you can measure the performance based on a set of test images. So that's kind of the way how you evaluate always the performance of what you have learned. Okay, and so basically, let's move on now to the current state of the art. What's the current state of the art? So what kind of approaches work well today? So what's the paradigm which we live in today? Basically what I said before is basically machine learning has become more and more important. And so basically the approaches here have to deal in particular with large scale, so have to take into account the large amount of images and videos around. And then something which is becoming more and more popular over the last 3 or 4 years is deep learning. And then something else which is very important is actually learning with noisy and incomplete data, right? So in many cases you don't always have the labels, and the labels might be incorrect. And in this case, you have to design machine learning approaches which can cope with this type of noise. And then the other thing which is very important is actually the data, right? Basically, if you give the machine learning approach bad data, then it will just train some crap classifier, right? And so basically, we have this large quantity of data around. But if you look at what you really want, it's not so much the quantity, but more also the quality, right? If you have noisy labels, the classifier goes wrong. So basically, how can you assure that the quality of your data is good? And A, you don't want it to be noisy, and B, the other issue, you want it to be diverse, right? If you have 10 times exactly the same car model, the classifier will not learn what's a generic car, right? And then another problem which I mentioned before is obviously the testing. You have to have a generic test set which is sufficiently general to be able to measure the performance well. Okay, and so basically, there are 3 points what people have done to address these problems. So manual annotation. So there was a large effort in the past years to annotate millions of images with mechanical Turk, for example, or other techniques of crowdsourcing. And the next thing is to use the noisy labels which are around and kind of try to tune them away. And then very recently, people started to use actually synthetic data, because that's a good way to actually generate examples with a variability and to assure that you can measure which kind of variability is around, okay? So once we have solved these two problems, the last part is how do we actually set up algorithms for machine visual perception. So what we want is have a complete understanding of the visual world, to take a video or an image, and you want to really know who is in the image or the video, what is the person performing, which object is it interacting with, which type of scene is it, okay? And so what is important here is how to design the models and how to set up the relations between the different components, and then also obviously want to go back to the data and the machine learning approaches to kind of have the interplay with these two components. Okay, and so one task which is very popular in computer vision is image classification. So what is the task? You have an image, and you want to assign to the entire image the labels of the objects which are contained in the image. So here we would have car is present, cow is present, and then all the other ones such as bike and horse are not present, right? And so there have been quite a lot of approaches which have been developed based on low-level feature aggregation, and the approach which is currently giving the best results is based on deep convolutional neural networks, okay? And so what is the idea of deep convolutional neural networks? Maybe you're familiar with it, but I just give a short overview. So what they do is they have a set of convolutions which they apply in several layers to the image, and then on top of that, they have fully connected layers which then classify the image. Thank you. And so here, one layer of a convolutional network. You have as input a patch. To this patch, you apply a set of filters, okay? And then you have a nonlinearity, and then some pooling mechanism, right? So each of the layers consists of these operations. The convolutional filters, so it would be just like a correlation filter, a template matching filter. They're not hand designed, but they're learned here, right? So the network learns these filters automatically. They're translation invariant, so the same filters are shifted over the image and obtain the relative same response. We have a number of filters at each layer. So here you have a whole stack of filters which are applied to an image patch. And then as you move up in the layers, you go from simple to complex filters, right? In the beginning, the filters have a small size. And then as you move up higher in the layers, due to the aggregations, you capture more and more complex structures. And all of this is learned jointly. And so I'll show in a minute that allows you to capture actually the structures in the images. Okay, and then I said, basically, once you have these filters, what's important, so these are just linear operations. It's important to apply some sort of nonlinearity. The simplest one is the sigmoid. And it has shown recently by using rectified linear units, you actually can improve the performance a bit because it simplifies backpropagation, makes learning faster, and avoids saturation issues. Okay, and then the last step is max pooling. So you can do average or max pooling. This makes this network invariant to small transformations. So basically, if you have a small shift, this pooling operation makes the network invariant to these shifts. And this allows to construct larger and larger receptive fields as we move up. Okay, and then basically, if you look at one of the first networks, which was proposed by Krzyzewski in 2012, it had 5 convolutional layers and 2 fully connected layers. Okay, and so the current architectures, they're all derivatives of this approach. So you can have more convolutional layers, you have different sizes of filters, more fully connected layers, and so forth. People have also started to play around and get away a bit from this classical architecture. And what's important here, that these models are very large. So you have a lot of parameters. So here you would have 60 million parameters, right? For each convolutional filter, which we have seen before, you actually train the weights. And to learn these large models, we need large training sets, okay? And then also it's very slow to learn. And so basically, successful was, and part of the success was due to the GPU implementation, right? So basically, why did it work? So these neural networks were around for a long time, and why did it start to work now? Was basically that now we have had these large data sets and the GPU implementations available, okay? And then, so what are these data sets? For example, there's ImageNet, which has 10,000, so the challenge is 1,000 categories and 1.2 million images, and the full data set is 10,000 categories and several million images. That was developed in Stanford, made it possible to train up this network. And if you look now at what these networks learn, so actually if you look at the first layer, what it does learn, it actually learns similarly to traditional edge and derivative filters, very similar filters, right? So if you look here, this would be different orientations for edges, some kind of color edge filters. So it's quite similar, but it's learned and adapted to the data set. And here, these are second-order derivatives, right? You can really see the first layer is very similar to the filters we traditionally use. But then if you look, for example, here at what is activated at the fourth layer, so here we show for different filters the highest response. So these would be the top 9 patches for a given filter with the top activation. So you can really see that these high-level filters, for example, here, they fire on dog faces or on other types of structures, for example, here on round structures. So they really learn higher-level representations. And then another problem in computer vision, so we have seen image classification. So what we want in the end, we don't only want to say what is the label for the image, but we also want to say what is the category and where is the category localized, right? So we would really want to say the cow is here and the car is here. So either we eliminate the object with a bounding box, that's what most people do today, but we can go even further and segment the objects out, right? So we really have a pixel assignment and say these pixels belong to cow and car. And so the state-of-the-art approach here, again, are based on the idea to first extract a set of regions from the image and then characterize these regions with powerful higher dimensional feature vectors, which can be either aggregated features or template matching here with the structured template matching, or more recently CNN features. Okay, and if you look at one of the approaches which is based on CNN features, what is the idea here? Here, you want to learn the proposals, so the set of regions which are likely to contain the object, simultaneously to classifying these proposals into one class. So either the object is present or it's not present. So you have the class object, car, cow, whatever, and then one class of background, right? And so what you would have here, you first extract these convolutional layers from the image. And then here, you train two different networks, a proposal network, a region proposal network, and the classification network, and they both rely on the same convolutional features, okay? And so here, the proposals, what you want is you want to determine regions which have significant content. And then here, for classification, what you do is you pool, you do Roy pooling of the features here in these regions, and then classify these proposals, okay? To determine what are the labels for these regions. And this allows you to say if an object is present or not. Okay, and so now I'll move on to something which is more difficult than just classifying images and detecting objects in images, is detecting objects and classifying in videos and classifying videos, okay? So video classification, what do you want to do? You want to assign an action label to a video clip, okay? So here, for example, you have the action answering phone. And then here, you have, for example, a birthday party. And so this is part of the TrackVid Multimedia Event Detection Challenge, where in a large stream of video, you want to find videos, for example, containing birthday party, horse riding, and different types of events. That would be, for example, something what people, users would want to search for, right? That's something which YouTube actually provides. They have mechanisms for providing different types of clips with different type of content. And so there, the state-of-the-art is based on dense trajectory features. And then there are also different types of CNN features. So for example, one approach developed the CNN features for optical flow. And another approach which is interesting is actually to develop convolutional networks which operate not only in 2D, but have convolutions in 3D and build hierarchy of convolutions in 3D. And I'll just step over the dense trajectory features. And so what is the idea here of these dense trajectory features? The idea is actually to follow points in the video. So what you really get is you get motion patterns in the video. So for a short amount of time, so in general it's up to 15 frames, you follow a point based on the optical flow through the video. So what is optical flow? Optical flow actually measures how the video stream moves over time, right? So if you have a point in the first image, what it says, what the optical flow says, is how this point moves to the second image. And there are different approaches for extracting optical flow. It's kind of a topic in computer vision by itself. And once you have this optical flow, then you can follow these trajectories in the video. And if you look at what you get, what type of trajectories you get, this would be the trajectories you get for this video. And what it really does, it really follows the objects through the video. And so it really captures the motion of points in the video, right? So once you have these trajectories, the question is what is the best way for describing them? And so here, this approach follows state-of-the-art approaches for image description. So it builds a grid around the trajectory descriptor and then measures the histogram of gradients, optical flow, and motion boundaries in these small grid structures. So it really captures what is contained in this trajectory. So for example, is there a strong motion? Is there a strong appearance change? And the motion boundary feature actually captures the relative motion. So it's the derivatives of the optical flow. It captures the relative motion of the object. So if you have an object moving in front of the foreground, this would be captured by the motion boundary histogram descriptor. And then you can aggregate these descriptors, for example, with bag of features. So you quantize your space, and you aggregate these features in local neighborhoods in the space. You stack them together, and then you can put a classifier on top of that. OK, and then if you apply that to video classification, obviously the visual information gives you a lot of information, but it's actually also interesting to use other features such as audio, OCR, or speech. So audio would just use it, for example, if you have happy birthday singing, that would be a very strong feature for recognizing that it's a birthday party. OCR, so it's optical character recognition. So for example, if you're making a sandwich, you could detect the characters on the different products and use that actually to recognize that somebody is making a sandwich. And speech would just transcribe speech to text and then use the text as an additional feature. So basically, if somebody is describing, if you have a video describing something, then you could use that to see what type of action the person is performing. And here just two examples of the approach, which are the highest ranked results for the event horse riding competition in the track with multimedia event detection challenge. And so these clips were found in 4,000 hours of video. So you have a small set of training videos. You have 100 training videos. You learn a classifier. And then you have this 4,000 hours of video. And then you have to search actually in this 4,000 hours of video, which are the most likely videos containing this horse riding competition. And then here just a few examples. So you can see here. And what's the main feature here for this task is actually the visual features, right? So you have a bit of audio, but it's not very significant. Okay, here again. And then if you look at another class, which is actually playing or tuning a music instrument, so here you can see basically the visual features are not very significant. But if you look at what the person is.
Now in this video, I want to show you how you can tune the first through the fifth strings to the sixth string, no matter what it's tuned.
And so it's clear if you have some transcription of the speech to text, then you can really use that to detect that these are videos where the person is actually tuning the music instrument.
This tuning allows for the greatest number of possible keys without retuning the string.
Okay, and last example. So then again, these were the first 3 ranked examples which the system found. Okay, and so this was for video classification. And then if you go back and think of the examples which I showed in the beginning, if you want to, for example, use action localization, action recognition in the context of cars, or for video surveillance, or even to just describe what's going on more precisely, you have to go one step further, as we saw for objects. You have to really detect and spatially and temporally where the action is actually happening, right? So you have to detect where the human is and which human is performing the action and over which time span, right? So this would allow you to precisely capture the environment, right? If you think of the pedestrian, you have the pedestrian who is standing and you want to see which direction he's walking when he starts to walk and when he stops, for example, right? And then here, one example, this would be brushing teeth. So you can see here basically different frames of brushing the teeth, and then here's the starting point, and then you want to detect the whole clip where the person is brushing teeth. And then if the guy goes out of the bathroom, you want to follow the guy, but you want to say the boy is no longer brushing teeth. Okay, and so what are current state-of-the-art techniques? So it's a quite difficult problem because you have to search in space and time, right? So you have these cuboids in space and time, so you have an infinite and potentially infinite search space. And so here, one approach which we have developed recently is based on first localizing action proposal in the frames, and then tracking them over a sequence of frames and determining the start and end position with the sliding window detector to see where the start and the end point is. Okay, and so here, how do we get the frame level candidates in each frame? So what we do, we extract a set of object proposals. It can be edge boxes or proposals which are automatically learned by the CNNs. And then for each of these proposals, we extract spatial features, but also motion features, right? And so what these motion features are, we have this localization, and for this localization, we extract optical flow, and then we can actually learn these motion CNNs, they learn actually flow patterns, right? So you can show that over a small number of frames, you can actually learn how these objects move and use that actually to classify the object as performing specific motion and to single it out. And then if you are in video, you have to kind of track these proposals in the video. And so here, what we do is we first take the top scoring proposal in the video, and then we use the class-specific information, which you get from the action classifier, but then we learn also an instance-level detector. So we describe each frame based on the real person which is there. So if it's like one person, if there are two persons performing the same actions, they can distinguish between these two persons and then perform a sliding window and select over time the best box, right? So we have one frame, we start with one frame, we learn the instance level classifier, so we determine this is the identity of the person, and then we track this person over the video. And by combining the class level and instance level detectors, we are robust to dramatic scale changes based on this class level information, and the instance level detector actually is model specific. And then once we have these tracks, we can use our dense trajectories to actually determine where the object is present in time. And then here, an example. So this is one of the state-of-the-art data sets for action localization. So here, in green, you see the ground truth, and in yellow, the detections. So you can actually see that it's localized accurately in space and in time. It's able to handle large viewpoint changes, which is actually a very difficult problem for state-of-the-art trackers and detectors. And then here, to illustrate what the difficulties are, here's one failure case. So here, basically, the intersection over union is not big enough. Here you have two people, and our approach doesn't manage to separate the two people correctly. And then the last is the confusion between playing football and playing basketball. Okay, and so basically we have seen, everything we have seen so far was trained with fully supervised annotations. So we had the examples manually annotated, and everything which we gave to the learning approach was correctly annotated. And so now, as I mentioned in the beginning, the question is how can we get away from this full annotation and move towards weak supervision? And so here, this is an illustration of one type of approach where you have the labels for the full image given, but then you want to determine automatically which are the recurring objects in the image. So here you have the labels car, for example, and then you want to learn where in the image the car is present. And so basically the different approaches, they're either based on multiple instance learning or matching based. And then another approach is basically based on learning this from videos. So if you have videos, you have more information, you have the spatial information where you can determine if the objects reoccur in different videos with the same label, but you can then also track the objects within the videos to stabilize the extraction, right? So you can basically say, these objects here are similar, then you can see, you can track them through the video, compare the tracks, and measure how similar the tracks are. So this allows you to get more information, to potentially get better localization and weakly localization. Okay, and then here for all these images, you have a collection of 100 images per class, but you only have the object label per video. And then here are the results showing that the approach completely automatically determined where in the video are the recurring objects, right? So all you need to do here is to give the image label, and then the approach can figure out where in the image the object is and learn an object model fully automatically. Okay, and now just to come to conclude with future research. So basically, as I mentioned before, what we really want to do is to be able to learn from this large-scale data where we only have weak labels. So these weak labels can be text, audio, or user click data. And basically here, we want to go away from annotating all this data, but to find ways of automatically learning and increasing our knowledge base, right? We don't want to, every time you want to learn a new object, annotate it and go back, but we really want to use this, leverage this data to learn object and action detectors automatically. And so basically the difficulties here are how to infer the latent correspondence from noisy labels. So you mentioned before, you can use multiple instance learning, discriminative clustering. And one approach, for example, is here, which we have developed recently, is to align images and videos with sound and text to really find the corresponding structures, align that, and learn what kind of matches are in the collection. And then another very promising avenue, which people have started to currently explore. So this is our recent approach we developed recently. It's going to be published at NIPS. And so here the idea is actually, if you want to recognize human actions or human 3D poses, so far we have only looked at human 3D poses, you cannot generate manually all this data, right? So for example, if you think of the space of actions, you have an infinite amount of different viewpoints and infinite amount of different changes of configurations. And plus, if you want to really model actions, you probably have to go to 3D to disambiguate different configurations, right? So basically, this is something, even if you had 100,000 labelers sitting in India or whatever, it would be impossible to annotate all this. And so basically here, the idea is to use the mocap information which is available. So we have mocap sequences for which you actually know the dynamics. We have these animations of mocap data, and combine this with annotated 2D images to generate a whole set of new images, and then use those to actually learn. For example, here what we did is just to learn the 3D human pose, but then ideally you would want to go even further and use this mocap data to animate whole sequences of actions, and then use those to learn the action labeling automatically. And the same thing, for example, people have been doing recently for cars. Instead of just filming many car videos, they have generated more data based on synthetic rendering and use those for training and testing. And the advantage here is basically that you can really model what you want to recognize afterwards, and you can assure also that you have a large variability of the space, right? Because if you just get the videos from the internet, you're not sure that they're similar or different, or you have to always measure how similar they are. While if you get the synthetic data yourself, you have a handle on how to generate it. Okay, thank you very much.
Very nice talk. Thank you very much. But one of the questions I had at the end, you showed the videos, and ultimately, when I look at the videos, they're still relatively simple scenes, right? So there's one moving object with a background that's relatively, simple. So how do all these, how do you perceive that all these systems are going to work when you have real complex scenes of many objects moving at the same time?
So this is actually a very good point. Most of the sequences which are around, they're very simple, right? It's often sports videos. And so my answer is twofold. So A, we have very recently tried to collect 2 different data sets with more real-world activities, right? And more application-oriented scenes, right? Because what you really want is to have, for example, my example of the pedestrian walking around. And so we have to start to collect these videos, which is obviously very, very, very difficult because, I mean, if you have images, it's relatively easy to annotate. While if you have videos, you have this problem of temporal annotation. So it's a demanding task. And so we have currently annotated 31 hours of videos, which took us almost a year. I mean, not continuously, but it took us a long time. And so basically, this has shown that some of the things work well. So for example, the spatial detection works very well, so that's actually not a problem. And the problem, what we have seen, was the temporal localization, right? So precisely localized in time, that seemed to be very difficult, and that's something we haven't really tested here at all, because the clips, if you saw them, they're pretty short, and all you had to do is to remove a bit of the boundary information. So that's something currently we're working on. I think to go further, you really have to create these realistic data sets, right? And so either you do it synthetically or semi-manually or something like that, but it's something we're currently working on. Yes?
Can you mention some of the big commercial success stories of where computer vision is being used in products that we use every day? Yeah. So I was wondering if maybe you could mention some of the current success stories in products that we see and use on a regular basis that are using computer vision now.
Well, I think there are quite several. I mean, I think I mentioned some of them in the beginning. There was like face detection, which you can see in all of the cameras. Then I guess in your house, people start to have now these surveillance cameras in their house. For example, Nest cameras, and there they detect when somebody moves up to their door. Then there's all the self-driving cars. So for example, cars now can actually detect obstacles, and they can automatically brake, right? So that's something which is definitely a success story. It has made things safer. And then all the visual search. So basically, I think if you now go on YouTube or Google or whatever, some kind of search engine, you can search for images. And maybe, I think we're just at the beginning, and I think as time will move, we'll get further and further. And another success maybe is the personal photos, right? So you can organize your personal photos visually. And as vision moves forward, I think all these applications can all go to the next level. And ideally, if you think of the application of video surveillance, I mean, it's kind of a controversial topic, but I think given what's going on today, it would be good if you could really have this abnormality detection and then just say there's something going wrong here. So that would be another application.
All right. What is the biggest challenge extending computer vision algorithms to work from images to videos?
I think that there are 2 challenges. One is just computational, right? I mean, basically you have to be sure that your algorithms run more or less in real time. And the second thing is, for today, people have in most cases just applied image-based approaches to video. And so in many cases, the full integration of the temporal component is still missing, right? So even if you look at what I've shown, I can show you a few examples where we actually use the motion information, but in other cases, we just use the frame-based information and glue the information together. And ideally, what you really want is to make full use of the 3D spatial temporal structure.
Hi. So there's been a trend for increasing image quality in terms of resolution, going from 2K to 4K, and people are exploring 8K resolution. And then we're going from 8-bit to 10-bit, and the cameras are getting better and better for signal-noise ratio, things like that. So are you aware of people studying the performance of the algorithms as a function of the image quality? And I guess another important one is frame rate. It seems like the higher frame rates might help the algorithms. But another aspect is with these higher resolution images, the edges are often not as sharp at the per pixel level. So there might be some confounding elements. So any comments on these aspects would be appreciated.
Are you talking about higher resolution by capturing the images or super resolution approaches?
Yeah, basically better image capture, higher quality for the image capture stage.
So I would say basically, so what we have observed that it has a huge impact actually on the quality of the results, right? Basically, so some of the current video data sets, they're still very low resolution with a lot of compression artifacts, and we started actually to apply like deblurring and stuff algorithms to make recognition easier, right? And that works. But as we move, and then basically one day I was like thinking, if you look at all these YouTube videos which are around now, they're all high resolution, right? And it makes your life so much easier. And the second thing of frame rate, so people have started to use these very high frame rate sequences. And again, so it's clear that if you have 100 frames instead of 25, for example, problems like computing optical flow become much easier, right? So basically, if you have a densely populated space in time, then things which, as tracking an optical flow computation, get basically trivial, right? So basically, it's clear by increasing this resolution in space and time, the approaches will, it will simplify our lives. It's very clear. If you look at the images I showed in the beginning, for example, this very small 200 by 200 blurry, noisy images, it was much more difficult, for example, to get clean edges out of that and to get them out of today's materials. So I think it's just positive. The only thing will be the computational cost, right? So basically, we have to get a handle on that, and if we can do that, then I think we'll just move forward to the next step.
Sure. Thank you for the talk. Very nice. Just back here. So you've looked, Cordelia, at visual features for action recognition. You've looked at motion. Also, your work has looked at pose, and a lot of other approaches have looked at pose. Could you comment on the relative importance of those three classes of features for action recognition?
So what are the three? Appearance features, motion?
Appearance, motion, and then pose. Say for human action recognition.
Okay, but I think they're not really orthogonal, right? Basically,
no, they're right, they're not.
They're not. Basically, so pose, the idea of our work on using pose was to have a finer representation of the action. And that's something I believe in. That was the slide I showed in the last part, right? If you have a good representation of the pose, it will help you, especially if it's 3D, it will help you to move to the next step forward, and then you can actually combine the pose with appearance and motion features, right? So I think the appearance and motion features, you can have them for the full image, you can have them for the human, and you can have them for the pose parts, right? And that will remain. And then obviously you can have any kind of combinations. But then if you have the pose, that's kind of the thing which we believe in, is then you can model the action much more finely. And if, for example, if you want to go towards things like temporal localization, you can really say at which moment in time the person brings the cup to the mouth, for example, right? So you get rid of all these low-level features and really have an abstract notion or a concrete notion of what's going on in your pose space.
Hi, Cordelia. First, I want to welcome you again to our conference. I hope you come to more of them. My question is with regards to this, ubiquitous use of deep learning in all these problems. It's still a very exciting time as far as that goes. People are still finding new applications and so on. But I'm also starting to sense a little bit of the asymptote beginning again, as we saw with neural networks back in the 80s. And I'm wondering, what's going to drive the next, leap in performance in that way? And an idea I have along those lines is that we're seeing these networks that are getting deeper and deeper. Microsoft has a 1,000-layer network or something. And, GPUs, well, they might double in speed every couple of years. What's going to drive it next? And one thing that occurs to me as a lesson from the brain, which certainly has a lot of layers, but it seems like forgotten in all of this, is massive parallelism. Okay, so we have a lot of layers, but we're not really looking in the direction of the kind of parallelism that the brain has. And I think also that we don't understand these networks very well. We're starting to visualize things and so on. And I think that's kind of lost because we have these sort of vertical networks, whereas if we have you know, a massively parallel layered mechanism, we might understand the functionality of each layer as well. And even when they're trained, at each layer there will be a natural identifiable functionality, as there are, you know, as exists in some of the early stages, at least, of the visual pathway in the human brain. I know that's a very many-layered question, but what about that asymptote that we're reaching?
So what do you mean parallelizing? Do you mean like the different layers, or you mean that everything is calculated from bottom up in the same way? I mean, because parallelizing can mean several things, right?
Well, I don't mean parallel, you know, up and down the layers. I mean in the old sense of, you know, suppose there's only one layer, but it's a massively parallel layer, and there's a lot of spatial interactions and that sort of thing across a very large grid.
Yeah, I think that's something it's clear. For example, one thing, I mean, like a simple example is what we cannot do. What we're not doing today, we're not increasing these networks incrementally, right? So every time you learn a new network, you change the architecture and you train from scratch, right? Nobody has thought of how, I mean, just a very simple example, right? How to build these things up. I have a student working on that now. How to build up these networks in an incremental way, and how do you add information? How do you manage that, right? That's what's going on in the brain, for example. Very concretely, you're not going to do reset every time you want to add an object to your collection. That's very clear. I think but that's not what you're looking for. Your question is more, where are we in 10 years, right? What are the problems in 10 years? Because it's clear that these things will saturate. You can make the networks deeper and deeper, and every time you get a few percent, but it's clear that that's kind of going to saturate. So what are the things which will not work? I think that's kind of the next level in the brain, right? How to put these different components together, right? I think probably you might have good object detectors. I mean, I'm not very familiar with the brain, but I know that at some layer you can actually you have a layer which detects different objects, which detects humans. But that what you really want is to go the layer, like the level beyond, to see really how these things interact, right? And there the question is, I think it's an open problem. How do you do that? Do you still have like graphical models, like you learn or train up graphical models and use that to model the structure? Or is there something else you need to model this? Or do we go back? Do we say basically enough of the deep networks and we want to go back? What we know how to do is how to construct models, how to put them together. I think that's kind of an open question, right? So I'm kind of more on the side. I want to understand what's going on and construct my own models and see how to integrate them. But then maybe in the end, there are people who want to train everything end to end, and that's maybe something which, if you have the right structure and you understand the structure, then you can do that. And I think that's what the brain does, right? It constructs its own structure, right? It's not just some bottom-up network which has fixed connections. It kind of builds the connections also on the fly, but depending on the data it is given. Okay.
All right, Cordelia, thank you for the wonderful speech. And we'd like to conclude with a small token of our appreciation on behalf of Lena and the entire organizing committee. We have a small plaque for you.
Thank you.
That's a souvenir from Arizona.
Okay.
Okay.
Let's come over this way so you can get your picture. Perfect.
Okay, thank you.
All right. Thanks, everyone. That concludes our plenary.